Well, looks like it's time to start, so the sign-up sheet is going around. Everybody make sure you sign in. If any of you are looking at the book between classes, then you will, we're going into Chapter 2, Section 3, 2.3 today. And if you've looked at it, you'll notice that a couple of the things we cover in this chapter we've pretty much already covered. We're still going to go through it. The first thing we're going to look at are the range and domain of each of the trigonometric functions. Does anyone remember from algebra, when you study of functions, what domain and range are? Which is which? You raising your hand or scratching your head? Oh, okay. Can anyone tell us what domain and range are for a function?
Range y and domain x.
Range is y, domain is x. That's as succinct a way of putting it as there is. The domain, the x and y graph, the coordinate axes are, you can think of them as the dependent and the independent variable. X is independent. You can pick any value of x you want. Once you pick the value of x, you have a dependent variable y, which is one and only one value at that x. The domain is over what values of x the function is valid or is defined. The range is how many values of how far up and down the y-axis can the values of that function go. So let's start with sine. And we know that sine of theta is the y coordinate, the y value. Now, over what value of theta, or if we want to write sine of x as any real number, is y. Over what values of x will that function be defined? Will that function give you a real answer, or give you a valid answer, a valid value? Anybody? Safely?
I'd say yes.
Yes. It will give you a value. Its domain is the set of all real numbers. Any value of x from minus infinity to plus infinity, every value of x, the sign of x is defined. It will give you a good number. Same is true with cosine of x. Well, now that's just going to get confusing. Go back to theta. Over what values of theta will this function return a legitimate value? Again, all real numbers. So the domain of sine and the domain of cosine are both all real numbers.
Is it true in cosine that cosine of y equals x? Sine x equals y equals x.
Yeah, that would. That depends on how you're defining your terms, but I don't want to get it. I don't want to get things any more confused than they are. We're talking about the domain. In this case, what's the independent variable? The independent variable is theta. The dependent variable is y. Again, the independent variable is theta. The dependent variable is x. So for every value of theta, for any real number theta, you will get a unique one and only one value of x. This is translating from radians into Cartesian coordinates, the x-axis, the y-axis. And remember the unit circle. What about the domain of tangent?
Numbers.
There you go. Remember when we talked about division by zero, it produces undefined results? In the case of tangent, anytime the cosine of theta is equal to 0, you're going to have an undefined result. So, when is cosine theta equal to 0? Anytime the theta is equal to pi over 2 or 3 pi over 2. Any odd integer multiple of pi over 2 will produce an undefined result. All real numbers except we ever graph these functions, then we'll see why that's the case. So, the domain of tangent is all real numbers except for odd integer multiples of pi over 2. Similarly, what do we find for the domain of the cotangent? Now the problem is it becomes undefined when sine theta is 0. So that will be at all integer multiples of pi. At 0 pi, at 1 pi, at 2 pi, at 3 pi. What is the definition of cosecant? 1 over sine theta. So, when is cosecant undefined? It's when sine is equal to 0. So, that would be, again, all real numbers except k times k pi, where k is an integer. And finally, we have secant. Is 1 over cosine theta. So when is cosine 0? At all odd integer multiples of pi over 2. Now, does everyone understand the domain limitations of each of these functions? Any questions so far? Okay, well, let's look at the ranges. Now, what's the range of a function? The domain is the x-axis, the range is the y-axis. So the range is all possible values of the function. So what, just right off at the top of your head, can someone tell me what the range of the sine function is? That's one end of it. Every time, no matter what value of theta you plug into sine, the output is always going to be somewhere between -1 and +1 inclusive. Okay, it'll be -1 at 3 pi over 2, and it will be +1 at pi over 2, and it will be somewhere between those two everywhere else. Is everyone familiar with that notation of the square brackets indicating it's a set notation? The square brackets mean the endpoints are included in the set. If they were parentheses, it would mean the endpoints are not included. So this is like saying or equal to, whereas the parentheses would mean not equal to. Again, what's the range of cosine theta? Exactly the same. -1 to 1 inclusive. Cosine theta is 1 at 0 and 2 pi and 4 pi at even integrals, multiples of pi. It's -1 at odd integral multiples of pi. And it's all other real numbers between the two everywhere else. What is the range of tangent? What possible values can you get from the tangent of theta? All real numbers. It goes from -infinity to +infinity. Now you'll notice that I put the curly not curly braces, parentheses. Why did I use parentheses here as opposed to the square brackets? No. What would happen in order for it to actually reach infinity? Cosine theta would have to be 0. And that 0 is not part of the domain. The answer would be undefined. So you can't actually get to it plus or minus infinity, but you can get arbitrarily close to plus or minus infinity. No matter how big a negative number or how big a positive number you got, you can always pick another number that the tangent will get you even lower or even higher. You just can't actually get there. Anyone want to take a guess at the range of cotangent? For cotangent? Yeah, it's just the reciprocal of tangent. So it's going to be the same. Now, it's going to get there. It's going to get closer to plus or minus infinity as sine gets closer to 0. But at 0, it becomes undefined, so you cannot get to plus or minus infinity. You can just get arbitrarily close. Hence the parentheses. You're up. Minus infinity to minus 1 and plus 1 to infinity. Will cotangent ever be 1? I'm sorry, cosecant? So 1 and plus 1 and minus 1 are inclusive. Another way of writing this would be x less than or equal to minus 1 and 1 less than or equal to plus x. So it's undefined anywhere. You're never going to get a number less than 1 as an output from a cosecant. What about secant? Same thing. That is the domain and range of all of the functions, and you can, all 6 of the trig functions, and you can see them summarized in table 4 on page 133. And we'll go ahead and touch on this again. Everybody clear on this so far? Domain and range. Okay. We've already looked at the period of these trigonometric functions, the periodicity, but the book covers it here, so let's go ahead and touch on it again just to make sure. We have a function let's say theta is what? Pi over 4. What's the sine of pi over 4? Anybody? Say again? 45 degrees. What's the sine? The sine of pi over 4, or 45 degrees. Wasn't it 1 over the square root of 2? What happens when you go a full 2 pi around and come back to this same point on the unit circle? You've got your theta is now what? 9 pi over 4. I hope I did that arithmetic correctly. But the sine, the function value is the same. So, a function, how does this book describe it? A function is periodic if there is a value p such that the function of x is equal to the function of x plus p. Then p is called the period of the function. In the case of these trigonometric functions, the period is going to be 2 pi or 360 degrees. Now, symmetry means that there might be other values of x that will also give you the same value. Plus or minus. But the fundamental period is, we know that for every value of x, if you add 2 pi to that x, it's going to give you the same function value. And that's the period of the trigonometric functions. And of course, since this is true for any x, it would also be true that and so you can, therefore by periodicity, p can be any integer multiple of p. And again, we've already looked at this. Let's just touch on it real quick, just to make sure. What can we know about an angle theta if we know the sine of the function? Or and by sine I mean plus or negative. I don't mean sine as in sinusoidal. If we know the sign of the function value, being positive or negative, then we know which quadrant we're in. If both sine and cosine are positive, then we're in quadrant 1. Here, if we're going to find that sine is positive and cosine is negative. In quadrant 3, we're going to find both sine and cosine negative. And in quadrant 4, you'll find sine negative and cosine positive. Each one is a unique combination that identifies which quadrant the angle lies in. So if I give you a problem where I tell you that sine of theta is equal to minus 0.5. And then I tell you that the cosine of theta is plus 0.5 without regard to anything else. What can you tell me about that particular value of theta? Which quadrant does it have to be in? Sine is negative, cosine is positive. It's got to be right here. Problem might turn this around on you. Or if the problem says that the sine of the angle is negative and it's in quadrant 3. You immediately know that the cosine of the same angle is also going to have to be negative. What if a problem tells you that the sine is negative, but the angle is in quadrant 2? What does that tell you? Pardon?
I'm going to be lost.
You're going to be lost, okay. What would this tell you if someone tells you the sine of the angle is negative? The value of the sine of that angle is a negative number, and the angle is in quadrant 2. No. No. This tells you, and whoever wrote the problem made a mistake, because you cannot have a negative sine value. The sine of the angle cannot be negative if the angle is in quadrant 2. It doesn't matter which way you go to get there, clockwise or counterclockwise. If you wind up in quadrant 2, the sine must be positive. Was it in this class or was it in the physics class? I think it was in my physics class yesterday. Got in and I started off the class asking if there were any questions about any of the homework, and immediately everybody in the class wanted to know about problem 53. What was wrong with problem? What was the deal with problem 53? Because the book, when they printed it, they printed the answer on the problem. They gave the question and the answer right there in the problem. Sometimes printers make mistakes. Sometimes the book makes mistakes. Sometimes your professors will make mistakes. When you see something like this and you know that it's not possible, make absolutely certain that you know that it's not possible, but if it's not possible, it's not possible. It would be the perfect time to start asking a question, saying, hey, how can this be? All right. Yeah, we can find the quadrant in which the angle lies. We've already looked at how to find exact values when sine and cosine are given. We've seen that, right? Hopefully this is just review for you, because we actually talked about this already in class, but again, I'm going to touch on it. If someone gives you the sine of theta is equal to 2, and the cosine of theta is equal to 3. What's the tangent of theta? Two over 3. Once you've been given enough information to know those two angles, sine and cosine, you've immediately got all the rest. Cotangent of theta, 3 over 2. Cosecant, 1/2. Secant, 1/3. Cosecant is the reciprocal of the sine. Secant is the reciprocal of cosine. Cotangent is reciprocal of tangent. Tangent is the ratio of sine and cosine. Once you've been given those first two functions, those first two values, you can now write the exact value of all 6. Just remember to keep track of sine. Again, boy, this is confusing. The polarity, the plus or minus, positive or negative sign of each value, because that determines the quadrant. Now, let's get to some what I think will be new information for most of you. Start talking about trigonometric identities. On the unit circle, radius equals 1. The sine of the function of the angle theta gives you the y coordinate. The cosine gives you the x coordinate. Pythagorean's theorem tells us that r squared is equal to x squared plus y squared, where r is 1, so 1 for every pair of points on the unit, for every pair of coordinates at every point on that unit circle, the sum of their squares must always equal 1. That's how you find out if a point is on the unit circle. If you take, if you're given 2 coordinates, to the coordinates to a point, you find out if it's on the unit circle by summing their squares. If they come to 1 exactly, they're on the unit circle. If they come real close to 1, but not quite, then they're almost on the unit circle, but not quite. But what is x? X is just the cosine of theta. And y is the sine of theta. And that is the first trigonometric identity. This is one that you'll want to write down. In fact, if you look at the covers, inside covers of your book, you're probably going to find a section that lists trigonometric identities. This will be the first one. Now I need to show you a little bit about standard notation. I wrote it this way in parentheses and squaring it so you would understand what this is. This is the value of cosine of the angle at theta squared. So if cosine theta is 1 over the square root of 2, then the square of that is equal to 1 over 2. All right, just squared, the value multiplied by itself. But the standard way of writing this, instead of using all the parentheses, is to simply write cosine squared theta. So, said all that just to point out that this means exactly the same thing as this. It's just a different way of writing it that avoids having to use all the parentheses. So when you see this trigonometric identity written, it's usually going to be written as cosine squared theta plus sine squared theta equals 1. Does everyone see how that works? How we got that? Here's the one they give us. In fact, I'm going to start over here. I'm going to put these identities over here. They give us another one here. They say tangent square of theta plus 1 equals secant squared theta. How would we get that? How could we prove that that identity is true? Well, we start off with sine squared theta plus cosine squared theta is equal to 1. As long as cosine theta is not equal to 0, and cosine theta, well, let's just leave it at that. Cosine theta cannot be 0, then we can divide everything by cosine theta, or cosine squared theta. And now what do we have? Sine squared over cosine squared is tangent squared theta. Anything divided by itself is 1, and 1 over cosine squared theta is secant squared theta. That's the second identity they've shown us. Using a similar process, we could also say that as long as sine theta is not equal to 0, cotangent squared theta plus 1 is equal to cosecant squared theta. Start out the same way, just instead of dividing by cosine squared, you divide by sine squared. We get a whole nother identity. We've also, and these are some other fun, they list them here on page 137. These are some that we've already looked at. Tangent of theta is equal to sine theta divided by cosine theta. Cotangent theta is equal to cosine theta divided by sine theta. It's the reciprocal of the tangent. And if tangent is the reciprocal of the cotangent, then the cotangent is the reciprocal of the tangent. Does everyone see how we get these? They're called trigonometric identities, and I don't think this is a complete and exhaustive list of them all, but they're certainly the most common ones that you're going to run into. This one especially. That one you're going to use a lot. Any questions so far? Okay, does everyone remember from algebra the properties of even and odd of a function, whether a function is even or a function is odd? Anybody? Okay. You have a function, f of x. If that function for a negative value of x returns the same value as it would for the positive value of x, then that is an even function. It would be an odd function if for a negative value of x, it returns the negative of the value of the function at x. Now, is a sine function, is it odd or even? Does the sine of negative theta return the same value as the sine of positive theta? Go back to our unit circle. Here's positive theta. Here's negative theta. What's the sine of negative theta? It's a negative number. The sine of positive theta is a positive number. So if we take the sine of negative theta, it's going to return the negative of the sine of the value we would get if we took the sine of positive theta. By this definition, sine is look again. Sine of negative theta equals negative sine of theta. So sine is an odd function. What about the cosine of negative theta? What's the cosine of negative theta? It's the same as if I took the cosine of positive theta. So here we see that the cosine of negative theta is equal to the cosine of theta. So the cosine function is an even function. What about tangent? Well, let's work it out. Tangent is sine over cosine. Sine is odd. Cosine is even. An odd divided by an even, well, it's a negative divided by a, so the tangent of negative, let's, you know what, rather than take that shortcut, let's work it out. Sine of negative theta divided by the cosine of negative theta is equal to the negative sine of theta divided by the cosine of theta, which is equal to the negative of the tangent of theta. So tangent of negative theta is equal to the negative tangent of theta. So tangent theta is odd. Cosecant of negative theta. What's the cosecant? The identities? The cosecant is the reciprocal of sine. So this is 1 over the sine of negative theta, which is equal to 1 over the negative of sine theta, which means it is the negative of the cosecant of theta. Cosecant of negative theta equals negative cosecant of theta, which makes it odd. Secant of negative theta. Secant is the reciprocal of cosine of negative theta. But the cosine of negative theta is equal to the cosine of theta. Which is the secant of theta. So the secant of negative theta is equal to the secant of theta. So secant is even. And that leaves cotangent. Cotangent of theta, of negative theta, is equal to the cosine of negative theta divided by the sine of negative theta, which is equal to the cosine of theta divided by minus the sine of theta, which is equal to minus cosine theta over sine theta, which is equal to the negative of the cotangent. Cotangent of negative theta equals the negative cotangent of theta. It's odd. And there will be times when you will be able to use the knowledge that these functions are either odd or even to help you solve problems. For example, how would you use the odd-even properties to find the cosine of minus 45 degrees. Because cosine is an even function, you know that it's also the cosine of 45 degrees, which is what? 1 over the square root of 2? What would be the cotangent of minus, what's the 3 pi over 2? Right there, we already know that the cotangent of minus 3 pi over 2 is minus the cotangent of 3 pi over 2. And what's the cotangent of 3 pi over 2? Where is 3 pi over 2 on the unit circle? Pi over 2, 2 pi over 2, 3 pi over 2, minus 2, it's 270 degrees. What's the cotangent? Here. No, cosine divided by sine, right? Cosine is 0, so it's 0. Kind of an anticlimactic result, but we still managed to use the odd-even property. So, do we have any questions? Got a couple minutes left. Any questions about the homework this week? Yes. Please, yes. Has anybody started looking at the homework yet? And if it's all just dead simple to you, that's great. But if you have some questions, it'd be a good time to start asking them. Okay, well, have a good weekend. I'll see y'all on Tuesday.